No. So when did you send me this Zoom update?
I'm not actually sure. Eric, are you able to see that screen?
Yep, it's not the presenter view, it's your actual desktop view. Or I guess the PowerPoint window itself.
You can see that, yeah.
Yep.
And what about now?
It still is just on your regular like PowerPoint
Slide?
window. Yeah.
It's not showing presentation mode?
No.
I can see it.
You're on presentation mode now. All right, so I have the pleasure of introducing Stephen Schwartz for the open part of his master's seminar today. We're going to get a look at his research he did from his master's. By the way, Stephen is from Noblesville, Indiana. That's a suburb of Indy. He's a graduate of Purdue. Hate to say that, but I overlooked the Purdue part when he came to school here. He was actually a very excellent student because Stephen is has the G.A. Ross Award for the top male student at Purdue. They only hand out 2 of those, top female and top male, and his name is inscribed on a pillar there for eternity. That award is based on GPA, activities, and leadership, all of which I can tell you Stephen excels at. He had a number of internships before he came to me. He did field scouting for advanced analytics. He did an internship at BASF at Seymour, and during that time, he actually roomed with some of my graduate students. It's how we sort of became acquainted. And then he also did an internship with Pioneer on soil health. So I can tell you, he has a great sense of humor. Because he actually understands and usually laughs at my jokes. And so it's a pleasure to introduce Steve today. He's going to talk about managing nitrogen availability for increased productivity of corn and soybean.
Thank you very much. I'm actually going to try to begin recording this video if that's all right. Still struggling with, there we go. Perfect. We are recording and we're good to go. So like Dr. Buelow said, my name is Stephen Schwartz. I'm very excited today to get to talk to you about the work that I've done through my thesis, and that is managing nitrogen availability in corn and soybean. So I want to talk a little bit about myself first and introduce you to myself. And that would be, so that is a picture of my dad and myself. You can tell me which one is which. I would love to know. I didn't grow up on a farm, but as you can see, I love hunting and the outdoors. My father has been an agronomist for 30 odd years now. And so my inspiration for being a part of the agricultural community comes from him. And he's a Boilermaker. His parents were Boilermakers. And so I had to go to Purdue University to get my undergraduate degree in agronomy and ag business. I think economics and science need to be joined together so we can have the right kinds of conversations for the best productivity, the best results for everyone. When I was at Purdue, fortunately enough, I met my wife. We were married last August. She has no agricultural background. She's a chemical engineer. But fortunately, we were able to bring her over into agriculture. She's going to be working for Bayer, making crop science chemicals in Iowa. So after graduation, we're going to be moving out to Iowa, and she's going to learn a little bit about agriculture, and I'm going to learn some more about chemistry. After my time at Purdue, like Dr. Buelow said, I came here to the University of Illinois, which is where I've had the absolute privilege to work under him in his research laboratory. I always put this picture up because it shows some of the scale that we have working on farmers' fields, doing these research trials in a way that can hopefully educate them, as well as provide them some good data, and we get to interact with them. This is actually from our Southern Illinois location. And so, like I said, I've had the privilege of working with all kinds of people in the industry and here at the University of Illinois. I've got to talk about corn and soybean, which is what I love. So today, just to kind of give you a roadmap of where we're going, there's two chapters that I'd like to address. The first one would be how yield level determines the corn response to nitrogen management. The second one being foliar protection applications to increase soybean yield response to nitrogen management. Now the question is, what ties these two things together? Hopefully it's obvious from the titles, that would be nitrogen. The question then is, why nitrogen? Well, it's an essential nutrient for crop growth. It's crucial in a lot of functions for the plant. Specifically for corn, it's the nutrient most often limiting corn grain yield. And as we think about nitrogen for soybeans, biological nitrogen fixation is really, really important for soybean production. So knowing how we manage nitrogen availability for both corn and soybean is important. Now, this is something you'll see throughout the entire presentation. I like to make statements and back them up with pictures. That's how I work. So we're going to do a little bit of an example of the importance and the value of nitrogen. So this picture, that is myself in the middle, Derek Lenzen and Marcos Loman. Those are the two guys I came into the crop physiology lab with. And I like to think of us as we're young, we're inexperienced, and that's what we look like without nitrogen. And so that was actually the first time the three of us ever met, was that picture right there at an ASA meeting in San Antonio, Texas. But this is what we look like when you add nitrogen. Look at that. We look healthier. We've matured. I've got more hair. That is the effect of nitrogen. Now, in all reality, that's the difference that a couple years makes on some graduate students. I had to include this picture because those two guys have had such an impact on my life and my time here at the university. I'm so thankful for them and for their friendship. And that was 2019 was our first ever meeting at ASA. And 2021 was the last ASA meeting that we will ever do together. So those guys were really, really important to me. And I hope this illustrates that nitrogen is key for growth and personal development, not just crops, but also personal development. So with that, we're going to jump into chapter 1 and talk about how yield level influences corn, nitrogen management in corn. So why do we need to manage nitrogen for corn production? Well, soil mineralization is a variable portion of the amount of nitrogen that can be supplied to the crop. It can support 50 to 80% of nitrogen, but it's not 100%. So we need to be able to manage the ability of the soil to mineralize nitrogen and provide nitrogen to the crop. The question then is, what factor has the biggest impact on nitrogen availability? And I would answer that that is the weather. There's so many influences that the weather has, whether that's leaching, which we can see from this picture, physical movement of nitrate down through the soil profile, denitrification, volatilization. There's all kinds of ways in which the weather and the environment is influencing our nitrogen management. But also, along with weather, corn is changing as well. Corn hybrids are changing and need better late season fertility. And we know that as much as 1/3 of the total nitrogen requirement of the crop occurs during reproduction. So we have these things in conflict: the weather influencing nitrogen availability and corn hybrids changing. So we have to manage them better. How do we do that? First off, I want to highlight nitrogen sources. We can change the fertilizers that we use. I'm going to be talking about polymer coatings on nitrogen fertilizer. We can change the placement of the fertilizer. We have banding is something that we're going to talk about today, placing it better for corn root access. And we can also change the time of the application. Maybe we can move that to an in-season timing to better match nitrogen availability with crop uptake. So I want to hammer in on each of these three in particular to kind of dive into why I researched them and just learn a little bit more about them. So when we think about nitrogen sources, for this study, we looked at urea and ESN. ESN is what we use as a substitute for polymer-coated urea. It helps control the release of nitrogen throughout the growing season. It does help reduce nitrogen loss to the environment through those mechanisms that I mentioned earlier. And hopefully, we can use this polymer coating to control the release of nitrogen and better match it to corn uptake throughout the growing season. It's kind of the idea behind using better fertilizer sources. But when we think about banded fertilizer placement, what do we mean? There are a lot of people that don't know what banding is. What we're actually doing is taking dry fertilizer and placing it into the soil profile about 4 to 6 inches deep, and we plant on top of that band so that we can have root access to that fertilizer late season. I love this picture. This is actually from one of the trials we did with you, Dr. Lee. That's some Nosebo product down there. And the roots are getting access to that fertilizer late season because of that banded placement. Now, there's some caveats with banding. It can reduce nitrogen loss to volatilization, and it can increase yields compared to broadcast, but banded placement is a costly practice to implement, and it can have inconsistent yield increases. We have to be realistic about some of the promised yield advantages that management may have. So we need to investigate this a little bit more. Not only placement, but in-season timing, right? This is doing a wide drop application to some B7 corn that we had this past year. But with even with in-season timing, it can improve nitrogen use efficiency and grain yield by matching that nitrogen availability to the crop uptake. But it's also an expensive thing to implement. Fuel cost of going across the ground, there's time that it takes, and it can be inconsistent when increasing yield. So there's more that we need to do to understand how these management practices work. So the research objective that we had for this trial was to identify these nitrogen management practices, both individually and in combination, and see how they can influence and optimize yield and nitrogen uptake. So to do that, we designed a trial in all of these locations. We had 3 locations: northern, central, and southern Illinois. Illinois is a very long state. There's a lot of variability from north to south. So we tried to capture that with these multiple sites. Now, if you look over on the left, you see rate, source, placement, and timing. And you might recognize those are the 4 R's: right rate, right source, right time, right place. We buried 3 of those. We kept our rate consistent at 100 pounds of nitrogen per acre. We used 3 sources in this trial: urea, ESN, or a 50-50 blend of urea and ESN, which we just refer to as blend. We also have placement. We either applied it banded or broadcast pre-plant. When we think about timing, we either had 100% of our fertilizer, dry fertilizer, applied pre-plant, or we did a 50% of our total nitrogen rate applied pre-plant dry, and then we came back and wide dropped the rest with 32% UAN at the V6 growth stage. So this gives us an ability to really capture a lot of the influences that these management practices have on the corn crop. All in all, we have 8 site years of this trial from 2019 through 2021. One of them had to be removed from the analysis. And when I was trying to look through these 8 site years, figure out what are we going to do with all this data, the first thing I tried to do was look at soil variability and try to characterize these groups by soil characteristics such as organic matter, fertility, pH. And when we did that, we weren't really reflecting the yield variability that we were seeing in each of these trials. And then I was like, okay, if soil data doesn't describe this, what about weather? Can we use weather data, precipitation, temperature to reflect this yield variability that we've seen? And again, that didn't reflect the yields that we were getting from these trials. So I dove into the literature and I tried to find a different way to analyze and break out this data. And what we came up with were these yield groups. So we broke down each of the sites into yield groups, a bucket, and we placed it there based on these characteristics. So we have a low yield group, which is any site that yielded less than 200 bushels per acre. And the average grain yield for the low site was 141 bushels, multiple sites right there. In the average yield group, that's any site whose average trial yield was between 200 and 249 bushels per acre, and that average yield was 209 bushels. Then we had the high yield group, which is any site that yielded greater than 250 bushels per acre, and that average yield was 261. So this is a post-mortem look at the yields and the responses that we have. I think it's really important to note here that these yield groups identify the cause of observed yield differences and are not used to prescribe managements because this is a post-mortem look. I can't tell you now what the yield is going to be at the end of the season here in Champaign. If I could do that, I don't think I would be here today. But that's why this is a post-mortem analysis of how these management practices influence yield and hopefully helps to better get an understanding of what these practices are doing, how they're influencing the crop. So I want to start off with working through the source, placement, and timing effects that we had. This is going to be kind of the layout for the rest of this chapter. We're going to have yield groups on the left, and then the factors are going to be across the top. And what we saw was in the low yield group, we didn't have any response to using enhanced fertilizer sources. Neither in the average yield group, there wasn't any benefit to using your the blend or ESN compared to just 100% urea. But when we move into the high yield group, we see that there is an advantage to using the blend in this high yield scenario. And there's a lot of factors that go into that. But one of the things we consistently saw when we were out in the field was this kind of a response. So on the left, we have ESN. On the right, we have the blend. Now, that may not look like a huge difference on the screen, but I like to get a top-down view of the approach. And this really shows us that on the right, we're seeing increased growth, greener plants, bigger leaf area. And that tells me the advantage of the blend is that it has readily available nitrogen right away at the beginning, right? So there's an advantage to the blend over ESN because it has that component that is urea to provide nitrogen to the crop right away. I like to think of it as the Goldilocks approach. The blend is neither too much nitrogen available up front or too much late season. It's just the right amount to provide nitrogen to the crop all season long. And then when we looked at yield, we also wanted to evaluate the nitrogen uptake, right? The total nitrogen that was consumed by the crop. And interestingly enough, you're going to see this throughout the entire presentation. It's novel. Greater nitrogen uptake is connected to yield. When these practices are working to increase yield and they're actually better supplying nitrogen to the crop, we get better yield. And that's what we see here. Again, the exact same thing with that blend increasing yield. Now, when we think about the difference between broadcast and banding, placement effect, I was expecting to see a more consistent response in every single scenario, especially when it comes to the magnitude of yield responses. But when we look at the low yield site, we had a 13 bushel yield response to banded placement. But in the average, again, this is a trend, there wasn't any yield advantage to using enhanced placement. But when we got to the high yield group, again, we saw this 4 bushel yield advantage. So as I looked at this, I thought, why wasn't there a greater yield response in the high yield group? Well, I believe there may be other limiting factors like phosphorus, potassium fertility, foliar protection that may need to come into play to maximize the yield. So there, think of Liebig's law of the minimum, right? There were other lower staves on the barrel that limited the response to banding in the high yield site. As we think about the low, having that fertilizer placement was so important because nitrogen was one of the most limiting factors for yield in the low yield group. And this is, again, what we really see with banding is the advantage of that early season nitrogen availability, right where the crop needs it. We get the plant off to a better start, which translates into mid-season growth. And we've even seen it translate really, really well into late season nitrogen availability, because as the plant's roots go down and proliferate to that band, it can have better access to the nutrition compared to when you apply nitrogen broadcast on the soil surface. And like I mentioned earlier, again, when we see these yield advantages with these nitrogen management practices, it is linked to an increase in total nitrogen uptake, showing that these practices are more efficient at providing fertilizer N to the crop. Now we're going to move on to our third main effect, that would be nitrogen timing. What's the effect of in-season applications on nitrogen yield? And interestingly, the low yield group was the only site in which we had a yield response to split applied nitrogen. When we looked at the data from this site, we saw that in the low yield group, that was when our soil was supplying less mineralized nitrogen than the average or the high. So it would make sense to us that the low yield group, which had less soil supplied nitrogen through mineralization, would respond better to in-season applications of nitrogen because you're picking up where the soil is lacking in those scenarios. And this is the kind of advantage we see to split applied nitrogen applications, right? It's that greening longer, keeping us healthier into that grain filling period. But it was interesting though, when I went and looked at nitrogen uptake, there was a slight difference in the trend. Yes, we saw the low yield group had increased nitrogen, but we also had increased nitrogen uptake in the average yield group. So though there it's not connected, what's going on there? When we dove into the precipitation data, we looked at early season rainfall in the low, average, and high yield group. We saw that there was, compared to the 30-year average, right? The low yield group had the greatest deviation from the 30-year average in precipitation. It was 2.5 inches more rainfall than expected. The average yield group was 1.5 inches of rainfall more than expected. And the high was basically the 30-year average. So that tells us that in those sites where we had greater early season precipitation, we lost more of that nitrogen early season. And so these side dress in-season applications of nitrogen were more advantageous to provide nitrogen to the crop. Even though there was more mineralization in the average yield group, that split application is still working to provide nitrogen to the crop effectively, which is what is reflected here. Now, those are the main effects of what we're looking at. Source, placement, and timing, but there was one interaction between these two that I wanted to highlight, and that's the interaction of fertilizer placement and source. And the main thing that we drew out from here was that in broadcast applications, using the blend was the most effective way to provide nitrogen to the crop. So if you broadcast all your nitrogen pre-plant, this shows us that having a little bit in urea to provide early season nitrogen and a little bit in a polymer coated source to control the release throughout the growing season consistently was better than applying all urea or all ESN. And when we look specifically at the low yield group, I was talking about providing late season nitrogen with the split application. I think that's another reason why we see this ESN treatment banded increasing yield the most, because it's 100% a concentrated band of ESN to control the release of nitrogen throughout the growing season for late season success. Well, whereas in the high yield group, it didn't matter what source you used when you were banding. There it was all about that placement method helped you increase yield. Now, even though it wasn't significant in the average yield group, again, we saw that this blend application when broadcast, again, trended to increase yield in the average yield group. That was extremely consistent across all of our yield groupings. So that's a lot of data. I want to break it down into some really easy key takeaways. When it comes to placement, placement was the only management factor to increase yield in multiple yield groups. That was the only main effect that was very consistent for us. When we think about timing, side dress applications improved nitrogen uptake when we had greater early season precipitation. Next, when we think about fertilizer sources, using the blend can improve yield in some scenarios, but it was really best when we paired it with a broadcast application over urea or DSN. That was where that fertilizer source was most effective. So in conclusion, nitrogen management uniquely influences yield in different yield environments, yield groupings. But the most consistent applications were banded placement of any nitrogen source or a broadcast application of the blend. So that's really what we saw from my research on core nitrogen management. Do you guys have any questions that you would like to ask about the first chapter before we move into soybeans? I know it's a different crop, so there's, I don't want to shift gears too quickly.
Ask if anybody on the chat.
Is there anybody
There's nothing
online?
on the Chat, but
If not, that's okay. We can move on. I just wanted to make sure before we switched crops.
I'll give us a chance.
Everybody had a chance.
As well.
All right. With that, I think we're going to move on to the second chapter, which is looking at how foliar protection applications can increase the soybean yield response to nitrogen management. So why are we talking about nitrogen on soybeans? We all know that soybeans get their nitrogen from fixation by the nodules. Well, when we think about it, only a portion of the total nitrogen requirement of the soybean crop comes from nodulation. We've looked at the data in past research showing that 50 to 60 or 55% of the soybean's total nitrogen requirement is provided through nodulation. So I think it's reasonable to say about 50 to 55% of the total nitrogen the soybean crop needs here in the United States comes through nodulation. So it's more accurate to say that soybeans get some of their nitrogen through nodulation. The question then becomes, how much nitrogen does the soybean crop need? Well, soybeans accumulate actually a lot of nitrogen, about 4 to 5 pounds of nitrogen per bushel, and only half of that comes from nodulation. So should soybean be fertilized with nitrogen? Well, maybe yes, maybe no, but it presents an opportunity to research it more specifically. And so with that in mind, we had this research premise. Soybean has a high nitrogen requirement, but nitrogen applications have inconsistently increased yield on soybean for a long period of time. But we believe that fertilizer placement and timing may be able to influence soybean yield differently when we pair them together with management strategies. Now, when I say management, we specifically focused on foliar protection for this research. Now, I know foliar protection applications, through past research, it's been suggested that you shouldn't make foliar protection applications of fungicide or insecticide without the presence of disease. We've seen that in past research. However, as a farmer practice, foliar protection has consistently increased yield. So there's a tension there and potentially an opportunity to research more and to learn about how foliar protection might increase yield and some of the scenarios in which it's most effective. So with that in mind, we have this objective to identify the optimal combination of nitrogen fertilizer applications and foliar protection to maximize soybean yield. And with that in mind, we designed this soybean nitrogen management trial. We had 5 nitrogen treatments. First of all, most importantly, an unfertilized control. Then all of our following nitrogen applications were 75 pounds of nitrogen per acre as 32% urea ammonium nitrate. After that, we had 2 applications at the pre-plant timing, either a broadcast or a band, and I'll show you what those look like here in a second. Or we had an R3 side dress application, either done mid-row with a coulter or wide drop. And again, I'll show you what those look like here in a second. So we had 5 nitrogen treatments, and then we had 2 soybean varieties in each year. So between 2020 and 2021, we had to switch out our second variety. We kept the same maturity group, but we had to switch them out because of some production differences, production changes. We also had 2 foliar protection applications, either none or Mirabis top and indigo applied at the R3 timing. And then we did all of these treatments across 3 irrigation methods: rain-fed, irrigated, and fertigated. Man, that's a lot of treatments. It's a lot of treatments. So I like to use pictures to break it all down. So we have 4 replications in this field. And as you can see, I've kept the treatments in the box on the first replication. That's just to show you we have each irrigated, rain-fed, and fertigated block. And within each of those groups, we have all of those treatments replicated inside. So we wanted to go back and figure out, okay, did the irrigation actually increase yield compared to rain-fed? right? Is there a difference between these blue and orange segments that we see here on the screen? And when we looked at 2020 and 2021, there was no advantage to using irrigation compared to rain-fed. There's no yield difference, it was non-significant, even though there was a very large difference in yield between 2020 and 2021, irrigation method didn't seem to have an effect. Even though in both years we applied basically the same amount of water, 2.5 inches and 2.25 inches in both years. So we applied the same amount of irrigation. We didn't see a response. I might be to blame for that. I'm not an irrigation expert by any means, but we worked with some professionals to help make these irrigation applications, and it didn't seem to increase yield for us. So when it came down to picking these treatments and how do we evaluate this study, right? There's a lot of interactions that we can look at. This is what we did. So we removed the rain-fed block, and we specifically focused on these 4 nitrogen treatments. The reason is we wanted to make a true apples-to-apples comparison between nitrogen, the total nitrogen applied, and irrigation water applied. Even though we didn't see a difference in yield between the rain-fed and the irrigated blocks, adding water or not adding water has influence on the soil microbial communities. And so I wanted to make sure that we were actually making a true apples-to-apples comparison. So it's more accurate to say that we had 6 nitrogen treatments. The 6th one being a root zone. That is that fertigation application, still balanced for 75 pounds of nitrogen per acre, all receiving the same amount of irrigation. But with the root zone placement, we applied 12.5 pounds of nitrogen per acre at every growth stage from R1 to R5.5. All of this was done across 2 varieties and 2 foliar protection treatments, like I mentioned earlier. So let's talk about these nitrogen treatments. What are they? Let's start off with pre-plant. When we think about pre-plant broadcast, that's kind of what it looks like from a farmer's perspective. We have a sprayer going across the field doing a weed and feed with some nitrogen in there. Now in the crop physiology lab, it's not quite as smooth of a ride. We don't really have air conditioning, but our spray boom still gets pretty good coverage on each individual plot. Now, when we think about our pre-plant banding, we do that using our liquid toolbar, and we're putting that nitrogen 2 inches beside, 2 inches below where we plant the soybean seed. So think of that like planter applied nitrogen. With these pre-plant applications, for me, the question arose, well, does pre-plant nitrogen actually increase soybean growth? What effect does it have? Well, we've seen pretty consistently, on the left, you see our unfertilized control. On the right, we have that 75 pounds of nitrogen per acre. And we have these growth increases. Now, I like showing pictures, but I said I like to back them up with data. So what we did was in 2020, we did a V6 canopy evaluation. And we started out looking at canopy coverage and NDVI. And we saw that both banding and broadcast increased greenness and our total canopy space compared to our unfertilized control. We did the same thing in 2021, but we only got a 2%, 3% increase in canopy coverage. So you might be asking yourself, Stephen, is that really a 2-year trend in bigger plants that we're getting from these pre-plant nitrogen applications? Well, sometimes the pictures that we take in the field to capture this data don't accurately represent what's going on the ground. And so we wanted to show you again, we see unfertilized control on the right, 75 pounds of nitrogen on the left. We did see a 2-year trend in increasing above ground growth with these pre-plant nitrogen applications. Whether that's the band or the broadcast, we saw that in both 2020 and 2021. Now, the logical next question is, well, Stephen, doesn't early season nitrogen decrease symbiotic nitrogen fixation? Aren't we affecting our nodules? So to answer that question, you have to go out in the field and dig. And so we dug a lot of soybean roots. And this is our group. We're out here rating the nodules, doing all these plant sample measurements. And we do all this so that we can get these pretty pictured soybean roots. So this is a V6 soybean root. That's our unfertilized control. And I actually remember the first time I ever went out into a soybean field to dig up a soybean plant for this study. I went out, I had my shovel, went to my first plot, shoved it in the ground, pulled the plant up, shook the dirt off the roots, and it looked like that. I had no idea what was going on. I went to the next plant, dug it up, shook the dirt off, looked the exact same. I was furiously digging in the field, trying to find a soybean plant that had nodules on the roots. I'd never seen soybeans without nodules. Well, it turns out that was our banded treatment, where we put that nitrogen 2 inches away and 2 inches below the seed. Interestingly enough, when we look at this broadcast application, that's still a healthy soybean root. So there's something going on here with these placements of nitrogen. So again, I like to show you pictures, but we quantified this with data. We did nodule ratings from 0 to 3, 0 being no nodules, which I never expected to see in my life, but I did. 3 being full nodulation. And we see that this pre-plant banded application decreased nodulation at the V6 growth stage in both 2020 and 2021. But at the R3 growth stage, we came back and did it again. Interestingly enough, any nitrogen application decreased nodulation compared to our unfertilized control. So these pre-plant applications we're making are having an effect later in the growing season. So some of the key takeaways we have here is, number one, pre-plant nitrogen increases early season growth. We would expect that. Nitrogen is essential for growth and development of these crops. However, our pre-plant band decreases nodulation at V6, but any nitrogen application reduces nodulation at R3. Now, speaking of R3, it's time for us to talk about these side dress applications that we made. I talked to a lot of farmers. They all tell me they love side dress. They love going out there, applying nitrogen to the crop or any fertilizer to the crop in season so they can match it with their corn, their crop uptake needs. Now, you might be looking at this picture and thinking, Stephen, those are not soybeans. Do you know your crops? What are we talking about here? Well, I actually did an extensive search on the internet, and I could not find one picture of a farmer applying nitrogen to his beans with a Y drop rig commercially. I think they're afraid of it. I think they're embarrassed that they're doing it and they don't want to show their neighbors. So for the first time, I'm not ashamed of it. I'll show you what it looks like to side dress soybeans. That's what it looks like. This is our, it's a little freaky, but we have our liquid toolbar applying both this Y drop application, and then set in front of each Y drop, we actually have a mid-row coulter it's a disc opener, so it opens up the soil, and we can apply nitrogen below the soil surface in between each of these rows. So those are our side dress applications. And we wanted to look at, again, we want to look at growth and nodulation. That's what we're trying to evaluate here. When we think about shoot biomass, we only did this in 2021 because our 2020 results were extremely shocking. So we wanted to add on to that research that we're doing so we can better quantify these differences. So when we think about shoot biomass, back to the pre-plant applications, we see both broadcast and banding increase our total shoot biomass at the R3 growth stage. At R5, we see the exact same trend. Even though it's not significant, there's not a significant difference between them, we see this tendency for pre-plant nitrogen applications to increase growth compared to our unfertilized control. But these side dress applications didn't have any impact on above ground growth. Even though we were applying nitrogen, 75 pounds, it didn't impact soybean above ground growth. Now, what about below ground? Well, so this is our root biomass at R3. And again, going back to pre-plant, we see this trend of our pre-plant applications increasing root biomass. And at the R5 growth stage, we see that the band had the biggest root system, the heaviest root system, excuse me, but we still see this tendency for pre-plant nitrogen to increase root biomass. Again, these side dress applications didn't have any effect on the growth, either root or shoot at the end of the season. So the question is, did they actually affect the crop at all? We'll talk about that in yield in a second. But I'm showing you all the shoot and root biomass effect. What about nodulation? What happens to soybean roots late season with the addition of all this nitrogen? Well, what we've seen is that these side dress applications, again, don't impact the nodulation, but the banded pre-plant applications will impact the soybean nodulation throughout the entire growing season. Setting it back early season has an effect late season, even though broadcast it's not different from the unfertilized control, and those side dress applications didn't affect nodulation compared to the unfertilized control either. So some of our late season takeaways: number one, pre-plant nitrogen applications affect growth all season long, but side dress applications didn't affect nodulation or shoot or root growth. So they may not have had an effect on biomass or on root proliferation or anything like that, but did they have an effect on yield? Did that nitrogen just go straight into the grain? So I always include this picture in all of my presentations. I think it's beautiful. It signifies it's time to load up. That's our soybean combine. It's time to go look at some yield data. And when we looked at the yield data, it's interesting. This is 2 years combined. We saw that none of our nitrogen applications significantly increased yield, except for our root zone application. Now, I haven't mentioned root zone in any of these nodulation or shoot or root measurements. That's because it, as a treatment, it didn't finish till R5.5. So the treatment wasn't finished, so we couldn't do any of those measurements on it. So we're getting our first look at this treatment as it relates to yield now, and it increased yield. But what happened in 2020 versus 2021? We mentioned that there was a big difference in yield level between those years. So what happened? Well, in 2020, we saw that the root zone did increase yield. And again, none of our other nitrogen applications worked. But in 2021, nothing increased yield. There was no benefit to adding nitrogen, even in this high yield scenario. This actually runs counter to previous literature. There's a lot of research that would suggest that at higher yield levels, soybeans might have a greater response to nitrogen above a certain threshold. But that's not what we saw in this data. So is that the end of the story? Or is there something more that we can understand about how management might be influencing these responses? And with that, I want to dive back into foliar protection, nervous top, and indigo fungicide and insecticide that we applied at the R3 growth stage. That is a great way to lose a lot of weight, is to spray in a Tyvek suit in the middle of the summer, which I've done my fair share of. But it was worth it because in both 2020 and 2021, foliar protection increased yield by 3 bushels. So that's a very consistent response across both years. The question is, how is foliar protection increasing yield? So I'm going to average both of these together to get one number, and we see the same 3 bushel yield advantage. Foliar protection is both increasing seed number and seed weight. So it's reducing pod abscission it's by helping that plant late season. And it's also increasing the photosynthetic capacity, protecting that leaf photosynthesis so that it can also fill out our seed better for heavier seed at the end of the season. So what impact does foliar protection have on grain yield? Well, without any foliar protection, we saw that none of our nitrogen applications increased yield. But this is where it gets really interesting. It's that with the addition of foliar protection, we start to see these nitrogen applications having more of an effect. Specifically, both that broadcast application pre-plant and the root zone application increased yield. Now, all of our nitrogen, well, both of our pre-plant applications, our mid-row, side rows, and root zone tended to increase yield. There was a tendency upwards, but there's also something going on with this Y drop application. It didn't have any benefit even with foliar protection. So let's dive into the quality, not the quality, the yield components, try to figure out how these nitrogen applications and foliar protection is influencing yield. When we first look at seeds, with the foliar protection, the interesting thing is with both the broadcast and the root zone, we are increasing seed number. So for our broadcast pre-plant, we've built a bigger plant early season. We have more nodes on the plant, and it's able to sustain a greater number of pods because we built a bigger plant early season. We think about this root zone application, we were spoon feeding it nitrogen throughout reproduction. So we were able to provide it the nutrition it needs throughout those reproductive growth stages to maximize seed number. But we look at the Y drop treatment, which I mentioned, and we had a decrease in seed number. So what I think is going on here is we're applying a high concentration of nitrogen directly beside the base of that plant. And I think we're shocking the soybean plant. We saw a downward tendency with nodulation, wasn't significant, but I think we may have quickly inhibited nodulation in this Y drop treatment and reduced the plant's ability to provide nitrogen to sustain these pods during reproduction. And I think that's also the case because when we look at seed weight, which is what we're looking at here, we see a little bit of yield component compensation, that +2 milligrams per seed in the Y drop treatment, which we see there. But again, with the foliar protection application, that broadcast pre-plant and the root zone application gave us heavier seed because we were, again, protecting it with foliar protection and providing nitrogen throughout the entire growing season. So in summary, broadcast and fertigation applications were the most effective nitrogen treatments. Our side dress nitrogen fertilizer, either mid-row or wide drop, really had little impact on yield. But adding foliar protection, that really optimized the soybean yield response to any nitrogen fertilizer that we applied. So in conclusion, safe placement of nitrogen fertilizer can increase soybean yield, but you have to pair it with a foliar protection application to take full advantage of that nitrogen and maximize your yield response. So with that, I wanted to add some acknowledgements for all the people at the University of Illinois who have helped me, Dr. Bilo, Julianne Seebauer, Jared Fender, Connor Civil, Peter Favaretto, Scott Foxhoven, Eric Winans, Logan Woodward. Those are all the PhDs that have had such an impact on my growth and development here at the university. Marcos Harmloma and Derek Lenzen, they came in with me as master's students. Dr. Mulvaney, I think you'll see Derek tomorrow. Marcos has decided to go on and continue with his PhD, so he's not going to be graduating with us. And again, Sam Laskanich and Darby Danzel, two younger master's students in the lab. And I'd also like to thank you, Dr. Milo, for being my advisor, Dr. Mulvaney, Dr. Lee, being on my graduate committee. And with that, I would take any questions that come from the Zoom, and then I'm sure we'll get to the questions that you guys might have for me as well.
There's nobody that's typed a question, Stephen, so.
Okay. I'll give you, if there's any questions in the chat, I would be welcome to field them. If not, we will move on.
Well, Eric says, nice job.
Thank you, Eric. Appreciate it. So with that, I will thank everybody for coming. Thank you for listening to my presentation. Really appreciate it. And we're going to move on to the private portion of the defense. Move forward with questions. Thank you, everyone. Appreciate it.
You can close down Zoom, but let's leave the